Hi kids, the first lecture in our new unit is on atoms, subatomic particles, conductors, and insulators, which hopefully are ideas that have at least popped up in another science class, but if not, we'll be introducing them from scratch here. So atoms were originally conceptualized as the fundamental building blocks of matter. Atom comes from the Latin root of unbreakable, so the idea was that if you took anything like a desk and broke it and broke it and broke it, eventually you would get down to one little tiny piece, and that little piece couldn't be broken anymore, and that was called the atom. There are 115 known types of atoms. These are called the elements. I'm sure you've seen periodic tables that show all of the different elements. We think there's more. We just have only discovered 115 so far. So this is that, object, that piece of matter. That's a scanning micrograph of a ant, and if you zoom in on that ant, you'll notice we've got little molecules, little pieces of matter, and if you zoom in even further, then you get down to this tiniest little piece of matter, which is the atom. So it turns out, though, for scientists, we're a little bit wrong. We can actually break atom into pieces as well, and we call those pieces the subatomic particles. Sub means smaller than atom. And there are 3 subatomic particles that occur commonly in nature. There's a lot more out there in space, but most of our matter is made up of the protons, neutrons, and electrons, which are also hopefully terms you're a little bit familiar with. This is kind of a classical view of an atom. We know it's more complicated than that now, but this is a good place to start. In the middle of an atom is a dense area called the nucleus, and the nucleus is where the protons and the neutrons live. So those 2 little subatomic particles are always stuck in the nucleus of an atom. The electrons are little tiny guys. They're zinging around the outside in orbitals, which you'll learn a lot more about in chemistry, but this is a good picture to start with. Each of these subatomic particles, the proton, the neutron, and the electron, has mass, which means it makes its own gravitational force field, and it has charge, which means it makes an electromagnetic force field as well. We talked a little bit about how gravitational force fields look. Electromagnetic force fields are similar. I like to view them as kind of a special kind of smell that every element or every particle that has charge contains, and that smell will allow those 2 objects to notice that they're there and to attract or repel each other. The 2 subatomic particles that we're going to be looking at mostly in this class are protons and electrons. We'll save neutrons for another level of physics. And this is a little bit of a table to help you compare and contrast some of the properties of protons and electrons. Protons have a lot of mass. They are relatively large compared to electrons, which only have a teeny tiny mass, almost 0, but not quite 0. Protons are always stuck in the nucleus of the atom, while electrons are orbiting freely around the nucleus of an atom. You'll notice a little asterisk there in the protons column. That's because that statement's not strictly true. There are some exceptions to the rule. You'll see some asterisks throughout this lecture and the next lecture because there's always exceptions in this world, but mostly they're always stuck in the nucleus of the atom compared to electrons. Protons are relatively stationary. We mentioned in the last unit that everything is moving around and jiggling. Protons don't jiggle very much. Compared to electrons, which actually can jiggle so much they actually move from atom to atom, so they can move all over the place. We define protons as having a positive charge. It's just sort of arbitrary, and electrons as a negative charge. What is sure is that those are opposite charges for sure, protons and electrons. And as you have maybe learned in popular culture or songs, opposite charges attract, which means this big proton is attracting that small electron and vice versa. The little electron is attracting the big proton because they have opposite charges. If you put 2 electrons near each other or 2 protons near each other, they're going to repel each other, which is a word for push away. So when you have two objects that have similar charges or alike charges, they're going to repel no matter what that charge is, and when you have 2 objects that have opposite charges, they're going to be attracting. That force, that push or the pull, the attract or repel force, is known as the electrostatic force, or Fe. We're not going to be getting the equation for that this year, although it's really not that hard of an equation, but I do want you to know some sort of fun facts about that force between the charged objects. For starters, it's the attractive or repulsive force between any two objects or particles that have a net charge. Really importantly, the electrostatic force is known as a fundamental force. Along with gravitation, it's one of the only 4 fundamental forces in the universe, which means those are really the forces that make up all the other forces that we've learned about. The strength of the electrostatic force has a direct relationship with how much charge the objects have. So the more electrons or protons that are present, the stronger the force is. That's pretty similar to gravitation. And it also has an inverse relationship with the distance between them, which means that the closer you force those objects to go, the stronger the force is. That is also very similar to gravitation. There's a lot of parallels between gravitation and the electrostatic force. Because the electrostatic force gets stronger the closer 2 charged objects get, objects actually never can touch each other. Every atom is surrounded by electrons, and those electrons repel other electrons, which means if I try to take my hand, which has atoms on it, which have electrons around them, and touch a desk, what's actually happening is the electrons in my hand are repelling from the electrons in the desk, and the harder I push my hand towards that desk, the stronger the electrons are going to repel. We're never able to actually touch anything because the electrons in one object will always push off from the electrons in another object. So hopefully that will rock your world a little bit. All the things you think you're touching in life, you're not actually, your electrons are actually just repelling their electrons. Turns out that all the other forces we've learned besides gravitation, so the normal force, tension, spring force, friction force, are actually just the electrostatic force. That normal force, for example, the 2 objects touching each other, they're not actually touching because the electrostatic force is repelling them. It's keeping them apart. It's pushing back. Tension is electrostatic force because the molecules in a rope, for example, all have electrons and protons, and so tension is actually the force between those electrons and protons in the rope. Same thing with spring force, same thing with friction. So those forces are all actually could be bundled into this category of electrostatic force. The behavior of the subatomic particles depends somewhat on the material or the atoms that they're in. And there's lots of properties of atoms that we could learn about, but we're going to focus in this unit on the property of conduction, or conductors versus insulators, and what does that mean about the movement or not movement of the subatomic particles. So in an atom, the nucleus stays put, right? The protons and the neutrons in the nucleus can't really move around, they're stuck, which means that the number of protons in a single atom is always constant. That number is the number that determines the element and also, these physical properties of the atom that we notice. So the color of something, a smell of something, a density of something is all determined by the number of protons that are in the nucleus. This property of conductivity is basically how easy or difficult it is for the electrons in that atom to move around from one atom to another, right? Those electrons are spinning around the outside, but they can actually go from one atom to another. Some substances it's really easy to do, and some substances it's really hard to do. So an insulator is a material that has low conductivity, aka something you could safely stick in a light socket. So if you could picture yourself doing this, then probably this object is an insulator. What's happening in an insulator is that the nuclei of the atoms are hanging tightly onto their electrons. They really don't want to give up their electrons, and they don't want electrons to move between atoms. They basically like to stay in their atoms. The electrons are moving around inside those atoms, but they can't easily escape or flow from one atom to another. So this might be a picture of an insulator. It has 9 atoms in this insulator. Each atom has its proton sitting there in the middle of the nucleus, and each atom has 1 electron. But you'll notice that each of those electrons is staying happily with their own atom. They're not moving from one atom to another, and they're certainly not getting off the insulator overall. So insulating materials keep their electrons. Some examples of insulating materials: wood, rubber, and plastic, right? Probably not the best idea to stick those in light sockets, but you're probably not going to electrocute yourself if you do it. In contrast, a conductor is a material that has a high conductivity, aka something you definitely shouldn't stick in a light socket. In a conductor, the nuclei of the atoms are happy to share their electrons with each other or with other materials that may be touching them. And electrons can move anywhere in the material. So they're not stuck in their atoms. They can move all around. They can easily move on or off of the material as well. This might be a sample 9-atom conductor. You notice we don't have the boundaries between the atoms because the electrons can easily flow throughout that conductor. Some atoms may have more electrons, some atoms have less. That's basically the way it looks inside of a conductor. A couple examples of common conductors: metal materials are conductors. Water, as long as it has some dissolved salt in it, is also a good conductor. In summary, the stuff around you is made up of atoms, which is made up of subatomic particles: protons, neutrons, and electrons. Protons and electrons have these two fundamental properties, mass and charge. We've spent a good amount of time on mass already. We're going to now get into this idea of charge, but both of those properties are conserved. Conductors and insulators are materials that have different electrical properties, and electrons move easily in conductors and not so easily in insulators. All right, I think that's it. Thanks a lot.